Alright, so like we said, we're dealing with the Taylor polynomials, and we said that this is just a way to find an approximation of something, like an approximation for sine, or approximation for e to the x, or approximation for natural log. So that's what we're working towards. Alright, so example 4. We want to find the Taylor polynomial of degree n equals 6, so a 6th degree Taylor polynomial, for f of x equals ln of x at c equals 1. Then use, this is the notation for the Taylor polynomial, so a Taylor polynomial of degree 6, to approximate the value of natural log of 1.1. So we know this is going to be important, and we know that this is important. So this tells us that we need to go to the 6th derivative. And c equals 1 tells us what? Yeah, the center of approximation is at 1, so it's not at 0. If it was at 0, it would be the what? Maclaurin, yes. But this is the Taylor centered at 1. Okay, so the first thing we need to do, we know f of x is equal to ln of x. Okay. We need to find up to the 6th derivative. So first derivative, f prime of x of ln of x is what? 1 over x. F double prime of x. Well, you could think about 1 over x as x to the negative first. So the second derivative is what? Negative x to the negative 2. Third derivative, 2x to the negative third. Fourth derivative, negative 6x to what? Yeah. Fifth derivative, and the 6th derivative. Alright, very good. So that's the original function and the first 6 derivatives. So now we need to evaluate each one of these at the center. Well, we know the center is 1. So if we evaluate each one of these now, ln of 1, sorry, is what? Ln of 1. 0. So Eric had talked about this yesterday. Why do we move that center of approximation for certain problems? Well, ln at 0, if you type that in, you're going to get an undefined answer. So we can't center this approximation at x equals 0 because we don't actually have a value for ln of x. So we have to move that center of approximation over to 1, and if we plug in 1, we have an easy answer. We know ln is 0 at that point. So we have a good starting point to start at. Okay, the first derivative evaluated at 1 is 1. What about the next one? Close. Negative 1. Third derivative. 2. Fourth derivative. Negative 6. Fifth derivative. And last? Okay, very good. Now again, thinking back to the Taylor polynomial, we found these derivatives and we found what they're equivalent to. So if you look back at the Taylor polynomial in your previous notes, what we actually found here was part of the coefficient term. Okay? So let's go ahead and we are going to find the approximation for ln of x. So again, we start with the first term. The first term is 0, and then we add to it each term afterwards. So the first derivative over the 1 factorial, second derivative over 2 factorial, and so on. We're going to continue on. So we know the original function evaluated at the center is 0. Now we're going to go to the second, which is the first derivative. We know the coefficient is 1 over 1 factorial. Again, you don't have to write the 1 factorial because we know what it is. And we can't just write x, we have to take into account the center. The center is 1, so it's x minus 1. So I'm going to erase this in a second, but I'm going to write, so this first term technically would be 0 over 0 factorial x minus 1. So it does fit the pattern, but if you have the 0 multiplied by everything, it's going to go away anyways. So that's why we just write 0. So it does fit the pattern. Next would be plus negative 1 over 2 factorial. X minus 1 for the center, but remember it's squared now. And then we have to continue on. We're going to write these out until we get to the sixth derivative. So the next one would be plus 2 over 3 factorial x minus 1 cubed plus negative 6 over 4 factorial x minus 1 to the 4th plus 24 over 5 factorial x minus 1 to the 5th plus negative 120 over 6 factorial x minus 1 to the 6th. Alright, so now we need to work on simplifying this a little bit so it's easier to find out what our approximation is. Eventually, we want to find the approximation at 1.1. Okay, so that's ultimately what we're looking for. And again, we have the setup as the Taylor polynomial. So because of what the Taylor polynomial says, this approximation that we're creating will be close, a very close approximation to what ln of 1.1 actually is. Okay, so let's try to simplify this a little bit. Well, the 0 is just going to go away. 1 over 1 factorial is just 1, so we're going to have x minus 1. If we have, well, we have the plus a minus 1, so we're going to have a minus. What is 1 over 2 factorial? Just 1/2. So 1/2 x minus 1 squared. We're going to have plus, if we can simplify, can we simplify 2 over 3 factorial?
1/3.
Yeah, 1/3. X minus 1 cubed. Anybody unsure how we simplified that? Or we're all good with that simplification? Okay. The next one then, so we need to have minus the negative 6 over 4 factorial. What does that reduce to? Minus 1/4. X minus 1 to the 4th. Then we're going to have a plus. We need to deal with the 5 factorial there. What does that reduce to? Pay close attention to your problem. Do you see something that's happening? X minus 1 to the 5th. Okay, let's go to the next term. We know it's going to be minus. What's that going to reduce to?
1/6.
Yeah, look at the pattern that's happening. 1/6. Yep. Okay, so we've gotten our problem to reduce down a little bit. We notice that it's alternating. We keep getting a plus and minus, plus and minus. But we also notice it's 1/2, 1/3, 1/4, 1/5, 1/6. So this is approximated to the 6th degree. But if they asked you to approximate it further, you know what the pattern is. You could keep expanding this pattern to get a closer and closer approximation. So now we want to use this here to approximate ln of 1.1. So now you can go ahead and get your calculator. It's going to be a lot to type in. Type in these values and get your approximation for ln of 1.1. I'll give you a minute or two to find that. So take your time. Make sure you're plugging in correctly. Find the approximation for ln of 1.1. Don't type ln of 1.1. Type in the approximation. Nice try, Eric. How did I know it would be you out of everyone? I know it's a lot of typing in, but did anybody get the value yet? Okay, let's hear it. 09531 what? Not one? That's not exactly what I got. You got a 1 there? Okay. What'd you get after the 1?
0, 1, 6, and 7.
That's what I got. So maybe somewhere you just rounded one of your answers before you calculated the next? Yeah, because it's a very small term, whatever was incorrect there. I mean, because you had the first few digits the same. So this is what I have as the approximation, 0.09531 01667. Okay. Did everybody else get that number? Okay, and if we actually type in ln of 1.1 into the calculator, you get 0.09531 01, and then it says 798. So we can see this truly is an approximation. We're not saying it's exactly the same, but to the 6th degree, that's a very good approximation of ln of 1.1. Now again, we could get this approximation closer to this if we continued the pattern and listed this pattern out further and further. We would get closer and closer to this value. So again, this is just another way to show that this truly is an approximation, but it's very, very, very close. Okay? Did you find an error then?
Yeah, I converted one of the fractions into a decimal, and then I cut off the decimal.
Okay. And again, it had to be very far out there because you had most of the digits the same.
Yeah.
Okay.
I just put 0.32 instead of 0.33.
Okay. So that's your final answer for this one. Are we okay with how we're using that approximation? Autumn, is that making more sense than yesterday was? Okay. Let's try example 5. Example 5, suppose that g is a function which has continuous derivatives and g of 2 equals 3, g prime of 2 equals -4, g double prime of 2 equals 7, g triple prime of 2 equals -5. Write the Taylor polynomial of degree 3 for g centered at 2. So degree of 3, that's important. Centered at 2, that's important. What makes this problem very nice? Yeah, all these steps we had up here in this problem, all of these derivatives and everything we evaluated, they just gave it all to us. We don't have to do any of that. They listed them all out right here. So all we truly have to do, and again, this is how you write Taylor polynomials, P. This is the degree, they said to the 3rd degree of x. So P3 of x for Taylor polynomial. And we need to just list out the Taylor polynomial now. So, why don't you guys give it a try and tell me what I should need to write. Do you guys need a minute to write it down and then you can try to tell me? Or do you think you have it now? Give you a minute to write it down? Try to write down the polynomial and then we'll see what you get for an answer.
You want us to expand it or just
What do you mean by expand it?
like all the x minus 2 squared to this time?
Leave that as x minus 2 squared. Leave it as x minus 2 cubed. Don't expand those. Now, you might be able to simplify your factorials after you write the original one. So with the Taylor polynomial, you always start out with the original value of the function at the center. So we know we're starting with 3. Do you have a question on them? You need an explanation? So with the Taylor polynomial, we start out with the original, then we go to the first derivative. So what's going to be my term for the first derivative? That's the original function. That's the original function. Now I want the first derivative term.
-4 times x minus 2.
Now, if I wanted to fit the pattern that you're supposed to have, what would -4 technically be over? 1 factorial. But it does simplify to 1, so you don't necessarily have to write it, but if you want to see the pattern. Okay, the second derivative, again, they give you the value for the second derivative. How are we going to fill in the polynomial?
7 over 2 factorial times x minus 2.
Very good. And the last one we will have plus -5 over 3 factorial x minus 2 cubed. And again, those factorials can simplify, so let's go ahead and simplify them. We already had this one simplified because 4 over 1 factorial is just 4. 7 over 2 factorial, what does that simplify to? Just 7 over 2, very good. 7 over 2 x minus 2 squared. And then, well, we're actually going to have a minus here. 5 over 3 factorial, what does that simplify to? 5 over 6. X minus 2 cubed. So what is the question asking for? Do we need to go further? Have we found the answer? What's the deal with the problem? What did they ask for? We're good? Yeah, all they asked, they didn't ask for any approximation, they just asked for the Taylor polynomial. So this is P3 of x right here, to the 3rd degree. And that's a simplified version of it also. So technically, this is the correct answer up here, but this is just a simplified version of it. To make a little more sense after that problem, Autumn, how we set it up. Were you having trouble with the original setup?
I thought the g of 2 equals 3. I thought that was the first one.
That is the original first function, like up here, from this problem up here. The original function was ln of x, and we evaluated that at 0.
Yeah, I was trying to put 3 over 1 factorial.
Well, this one would technically be 3 over 0 factorial, which is still 1. So that's why it's 3. Then the first derivative is over 1 factorial. Second derivative over 2 factorial.
That's
So,
why I was confused, because I was like, well, why'd they give us
Okay.
derivatives if we don't even need
Yeah, the pattern starts with 0 factorial. Because 0 factorial and 1 factorial both come out to be 1. Okay? Alright, let's take a look at example 6. Use a third degree Taylor polynomial or approximation of e to the x for x near 0. So if they're saying near 0, what do you think that means? They want the approximation. Well, it says near 0. If you evaluate e to the 0, what do you get? That's a nice value. So they're really telling you here that they want the center to be 0. They say near 0, but if you actually plug in 0, it's a nice value. So they want it centered at 0. So we're using this third degree Taylor approximation to find the limit of this. Right here, e to the x minus 1 over 2x. Then we're going to compare it to the actual limit at 0. And then see if our results are surprising. Why or why not? So first thing is third degree Taylor polynomial. So we have to do what we know. The original is e to the x. And we need third degree, so we need 3 derivatives. What's the first derivative? I like this one. What is it, Cameron? E to the x. What's the second derivative? E to the x. Third derivative. E to the x. I like this function. Nice derivatives. If we evaluate them at our center, at 0, we get what value? We already mentioned it. 1. Okay? So ultimately what we're trying to do is we want to find this limit of this. But we want to approximate this e of x. So in this limit, we're finding an approximation for this e to x. And the approximation that we find, we're actually going to plug into that e to the x. So we're going to find the approximation of e to the x. We know the center. We have the derivatives up to the third degree. We have all the information to fill in the Taylor polynomial. So how are we going to fill this in? What's it going to look like? And I'll write it with the pattern. That way it's easier for everybody to see. We start out with 1. Remember, it's over 0 factorial, which does simplify to 1. The next one, you said plus 1. It's going to be over 1 factorial. What goes with it? X minus 0, which is just x. So if it's at the center, remember, you just put x, and it's to the first power. Plus what? 1 over 2 factorial x squared. So we're just writing it to fit the pattern. Plus 1 over 3 factorial x cubed. So that fits the pattern of the Taylor polynomial. And we can reduce it a little bit. Like we said, 1 over 0 factorial is 1. 1 over 1 factorial x is x. Eric already told us 1 over 2 factorial is 1/2 x squared. If we simplify the 1 over 3 factorial, we get 1/6 x cubed. So that's the approximation for e to the x if you go to the third degree. Are we okay up to that point? So now they want us to use this approximation to help us find the limit. So I think I'm going to need some room, so I'm going to erase a little bit. I'm going to erase these derivatives over here. So the limit as x goes to 0, and instead of writing e to the x, we're filling in our approximation. So we have 1 plus x plus 1/2 x squared plus 1/6 x cubed, and then there's a minus 1 up there, over 2x. So again, we're using the approximation for e to the x to find this limit. Before we take the limit, we're going to simplify this a little bit. So let's kind of do 2 steps in one here, just to make simplification a little easier. When I have 1 minus 1 here, do we see those 1s are going to cancel? I have this one here and this one here. Those are going to cancel. Then what's in common in the top? What do they all have in common? After the 1s go away, because they cancel, an x. So I'm going to do the 2 steps in 1s. I cancel those, and I'm going to factor out that x. That way I just save myself some writing. Okay, so canceled the 1s, pulled out an x. Good so far? Alright, what else can happen now to simplify? X's can cancel. Okay. Now we want to take the limit as x goes to 0. As x goes to 0, what's the limit as x goes to 0? Anybody know what the limit is? Yeah, if you plug in 0 to take the limit, you would be left with 1/2. So that's the limit with our approximation. Remember, we approximated e to the x. So we found the approximation with the limit. Now compare it to the actual limit at 0. So what we want to do now is take the limit as x goes to 0 of e to the x minus 1 over 2x. Well, what happens if we try to evaluate the limit as it is? Yeah, we would get 0 over 0. Doesn't work. So what rule can we use to maybe help us evaluate this limit? Yeah. Okay. L'Hopital's rule. So we can take the limit. X goes to 0. And it would be of what now? Remember, derivative of the top, derivative of the bottom, so we're left with what? What's our new fraction? E to the x over 2. If we take the limit of that now, as x goes to 0, the limit is what? 1/2. Is this surprising? Okay, so what we showed is that our approximation was close enough that our approximation could represent e to the x, close enough that the limit is actually the same. So it's approaching the same limit. So we know our approximation is actually a good approximation since our limits are the same. Okay, so this is the true approximation of e to the x. Now again, this approximation could get better and better the more terms that you go, but this is only a 3rd degree Taylor polynomial. But we can see that the approximation is close. Any questions? Alright, so I'm trying to decide where to go from here. We see we have 1 page left on the back of notes. I think what I want to do for this, I know we still do have some time left today, so I think maybe we'll talk about example 7 today, since everybody's here. And then we won't have time to go through example 8. So I'll go through example 8 tomorrow. And then if you're not here tomorrow, I'll go through example 8 with you on Friday if you're not here. That way we can plan on probably having the quiz so everybody's here together on Monday. And then any time tomorrow that we're done with notes, if you're here, would be homework time, ask questions, get ready for the quiz, study your note cards. Friday, if you're here, would again be a study day, practicing those note cards, because again, 3.2, all of those tests are going to be on this quiz. So you need to study those, look back through homework. And then if you weren't here tomorrow, I can go through example 8 with you on Friday. And then everybody can have some time to prepare for the quiz 3.1 through 3.3 for Monday. Okay, sound like a plan? All right, so let's look at example 7 and we'll wrap it up there today. So example 7, given that, again, this is a Taylor polynomial of degree 2 here, so a plus bx plus cx squared is the second degree Taylor polynomial for f about x equals 0. So when they're telling you x equals 0, what did they actually tell you here? Yeah, the center is 0. It's a Maclaurin series. The center is 0. What can you say about the signs of A, B, and C if f has a graph pictured to the right? Justify your answer. So we have a graph here. We just want to be able to determine, are the coefficients positive or negative? So how can we figure that out? We need to justify our answer, and we need to determine whether they're positive or negative. So A, B, and C, we want to know whether they're positive or negative. Anybody have any ideas on any of those? C has to be negative. Why do you say that? Okay, so we see the original one's concave down, so we know this that C has to be negative. What's another way to determine the concavity? So you talked about the concavity, but that deals with... Yes, that's what I'm going for. Second derivative, and at the second derivative, okay, so it is negative, so f of x is concave down. So that's like your second derivative test. It would be negative, that means the original is concave down. Very good. Just from the picture, looking at the picture, can we determine what A would be? Is it a positive value or a negative value? Okay, I agree. How do you know it's positive? What is A? A is what? Sorry, Eric? Okay. Kaylin, what were you saying?
I was just going to say the y value that it crosses is above the x-axis.
So it's kind of out of order, but the A is actually your y-intercept. So it's just asking where your y-intercept is. So your y-intercept, is it positive or negative? Well, it's above the x-axis, so it's positive. So this is just your function value. And it's positive. F of x above x-axis. Okay. What about B? How can we determine if B is positive or negative? Maybe try to think of it along the same lines that Eric thought about for C. But how can we determine for B? If C is the second derivative, what would B be? First derivative. So we know this is going to be the first derivative.
Positive.
What do we know about the first derivative?
Positive.
Yeah, we know it's going to be positive. F of x increasing. So we were able to determine A had to be positive, B had to be positive, C had to be negative. Another way to think about this, A, if you think about it as Taylor polynomials, your A value, which is the value of your original function, is the value of the original function. So we're saying the center was at 0, so whatever the function is evaluated at 0 over 0 factorial. 0 factorial we know is positive, so determining whether A is positive or negative all determines what your function is at that value. Well, we said the function at that value was positive, it was above the x-axis. Your B value is your first derivative. B is the first derivative evaluated at 0 over 1 factorial. Again, we know 1 factorial is positive. it all determines whether the derivative at that point 0 is positive. So at point 0, x equals 0, we looked at the derivative. At that point, the derivative was positive, so we know b had to be positive. C, which is your second derivative up here, f double prime of 0 over 2 factorial. Again, 2 factorial is positive. It all depends on what the second derivative at that value 0 is. Well, Eric told us from looking at the graph, we're able to determine it's concave down, so we know that the second derivative at 0 has to be negative. A negative over a positive makes our C value negative. So this is just 2 different ways to look at how we found our answers. And that's all they're really asking for example 7, just being able to analyze that and try to determine if your coefficients are positive or negative. So we'll continue on with that tomorrow. We'll do example 8, and if you're not here, I'll go over example 8 with you on Friday. You have a few minutes left.